Today we are going to look at trig equations that require the quadratic formula or that can be solved by factoring. Suppose we want to solve the following example problem. So we want to solve for x. So we get the cosine of 2x is equal to the sine of x. And you want the solution for all real values of x. Well, the first thing for us to do is to reconcile that we have a double angle formula involving cosine, and that's equaling the sine function. So we're going to have to make a decision about how to proceed here. One of the benefits of having cosines and sines is that there are so many identities that relate to the two of them. If we start with the double angle formula for cosine, that is equal to the cosine squared x minus the sine squared x. I always encourage my students to remember where that equation is derived from. If we start with the sum formula for the cosine of two angles, cosine of x plus y is equal to the cosine x cosine y minus the sine x sine y. If we let y equal x, then this problem becomes the cosine, or this equation becomes the cosine of x plus x equals the cosine x cosine x, because y was replaced with x, minus the sine x sine x. And that simplifies as the cosine squared x minus sine squared x. So many of the identities, if you can remember where they come from, you can rederive them in the event that you happen to forget this. Next, let's use the Pythagorean triple, or the Pythagorean identity that relates cosine squared and sine squared, namely that sine squared x plus cosine squared x equals 1. Since this original equation involves solving an equation that's set equal to the sine x, it would be beneficial if we can rewrite this cosine squared x minus sine squared x expression strictly in terms of sines. And that can be accomplished by taking, in this Pythagorean identity, solving for cosine squared x, and we get 1 minus sine squared x. So when that gets substituted in this double angle formula for the cosine of 2x, finally we're able to rederive the cosine of 2x as 1 minus 2 sine squared x. Again, if you can remember this, where it comes from, it's a lot better than trying to remember it. Because as we move away from this particular subject, memory fails, and we may forget it. We may remember it incorrectly, but we can always derive it and see whether the equation makes sense or not. So this original example that we have up here can be rewritten as the following equation, solving for x for all real values of x. 1 minus 2 sine squared x equals sine x. This is a quadratic in sine of x. The way we solve quadratic equations are either by factoring, and we can apply the zero product property, or by using the quadratic formula. In any event, both require that we have this equation set equal to 0. So if I take this equation and move everything over to one side, I can get as the following quadratic equation: 2 sine squared x plus sine x minus 1 is equal to 0. This appears to be factorable. What I think about is, say, if I were to let u equal sine of x, then I can get an interesting quadratic in u. This is clearly solvable by applying the factoring and then the zero product property. I would factor this quadratic as 2u in u, and a positive 1 and a minus 1. We'll verify that it produces a linear coefficient term of 1. This is negative 1u plus 2u is positive 1u, so this works. With this substitution, realizing that u has the same role as sine of x, we can factor this quadratic in sine x as follows. 2 sine x minus 1 multiplied by sine x plus 1 equals 0. Therefore, the two solutions are sine x equals positive 1/2 or sine x is equal to minus 1. To solve problems involving integers, integral values, 0, -1, 1, and I guess 0, 1, and -1. Those are the main values that I think about. You can think about the unit circle. I personally like to look at the sine graph and just think about where this happens. We know what happens here at 3 pi over 4 radians. 3 pi over 2 radians, rather. If I were to draw one more cycle in this direction, this would correspond to an x value of negative pi over 2 radians. So solutions where the sine function is equal to negative order are infinitely many, and I can simply choose one. I can choose one that's in the principal branch of the sine if I wanted to, if I were interested in solving this by applying the arc sine, or I can pick this value here that's in 3/4 of the way around in complete revolution. So of course in the context of the unit circle, we're talking about the negative y direction, the negative y-axis, so that would be 3 pi over 2 radians. So it really doesn't matter which one you choose. I'm going to go with the negative pi over 2, and I'm going to say one set of solutions, which would be indexed to integers, would be negative pi over 2, as well as every even multiple of pi. And k, in this case, would be an integer. So we're going to use this symbol. This is the symbol of integers. This obviates the need of having to include a plus or minus sign, because integers include positive integers, positive whole numbers, 0, and negative natural numbers, if you will. So we don't need to put a plus or minus sign. The next solution that we have to solve is sine of x is equal to 1/2. So the sign is positive. We know that happens in two quadrants. So the two quadrants are the first and the second. So some values of x here could be in the first quadrant, opposite over hypotenuse. We recognize this as a 1, 2, radical 3 right triangle, which is our famous 30, 60, 90 right triangle. Sine is also positive in the second quadrant. This is opposite over hypotenuse. This would be negative radical 3. So these reference angles would be either pi over 6 radians. It's opposite the smallest side, therefore it's the smallest angle, which corresponds to 30 degrees. And another set of solutions would have a reference angle of pi over 6, which an angle in the second quadrant would be pi over 6 short of a complete pi, so it would be 5 pi over 6. And again, we're talking about even multiples, integral multiples of pi. Or again, k is indexed to the integers, and again we're indexing it to the integers. If you want to index it to the whole numbers, you can, and all you need to do is include a plus or minus sign. Thus we have our 3 series of solutions, our 3 sets of solutions consisting of 3 elements, all of them indexed to the same parameter k, which are integers. So the first set of solutions, our x of k is equal to negative pi over 2 plus 2k pi, where k is an integer. That corresponds to solutions to the form sine of x is equal to -1. And then we have solutions of the form x of k is equal to pi over 6 plus 2k pi and 5 pi over 6 plus 2k pi, and those are solutions to the equation sine of x is equal to 1/2. I hope that was able to help you solving these quadratics. Thank you.